Welcome to Ask and Learn.
Okay, so in this problem, we have an air standard cycle with three steps or three processes. In the first part of this problem, in part A, let's put in here, we have to make a sketch of the PV and TS diagrams of this cycle. So let's begin, first of all, enumerating the process. So from point 1 to point 2, we have a process with V constant, with constant volume. From 2 to 3, we have a process with the temperature constant, and the final process is from 3 to 1, when we have a process with constant pressure. Okay? So knowing what is the main important thing in this process, each one of this process, we can make first of all the PV diagram. So let's begin. Put in here what is going to be the PV diagram. And for the PV diagram, we have here the point 1, and point 1 from point 2, we have V constant. Therefore, we go, here is point 2, this is V constant. From point 2 to point 3, we have hyperbole, which is constant temperature. Let's put in here. Let's put in this way. We have constant temperature. This is point 3. And from point 3 to point 1, we have constant pressure. Okay, so the direction of this process is this one indicated by the green arrow. Okay, so we have the values in here. So we know that this volume is V2 and this volume is 7 V2. We know that this pressure is 100 kilopascal, and this pressure here is 700 kilopascal. So this is the PV diagram. Now the TS diagram is going to be, let's put in here, the TS diagram. Well, uh, an isotherm, an isotherm path in a TS diagram is represented by a horizontal line. So we have here the 2 from 3 is going to be a horizontal line, and we know that the constant pressure or constant volume in a TS diagram is represented like this. So this is going to be, this is 1, this is 1 from 1 to 2, and this is going to be from 3 to 1. Okay, so this is the PV diagram, and in the left, in the right side, we have the TS diagram. So this is the first part of the problem. Now, in item B, we have to find the ratio of the compression work of the expansion. Sorry, we have to find the ratio between the compression work with the expansion work. So what we want is basically the division between the compression work with the expansion work. Therefore, what we actually want if we look in the PV diagram, the compression work occurs from 3 to 1, and the expansion works occurs from 2 to 3. Okay, so this is the steps when we have compression and expansion. And one from 1 to 2 we do not have any work because the volume does not change. Therefore, let's see. To calculate the work 3-1, the 3-1 work is just negative the integral from 3 to 1 of P dV. Therefore, this is just minus P, which is constant, V1 minus V3, which if we use the ideal gas law, we can say this is just negative R T1 minus T3. And to find what is the temperature 3, we must remember that the temperature 2 should be equal to temperature 3 because they are in an isothermal path. Therefore, if we use the ideal gas law, we can say that T2 is going to be equal T1 P2 divided by the pressure 1. Therefore, this is just 300 times 700 divided by 100, which gives us a temperature that is going to be equal to 2100 Kelvin. Okay, so let's finish the work 3-1. So the work 3-1 is going to be negative the value of the constant R, which is 0.287. That multiplies the change in the temperature, which is 300 minus 2100, and that's precisely 516.6 kilojoules per kilogram. So that's the work 3-1. Now that we have the work 3-1, we have to find the work 2-3. So the work 2-3 is going to be the integral from 2 to 3 of P dV. Since this is an isothermal, we need to use the ideal gas law and change the pressure for the temperature. Therefore, this is just RT divided by V dV. If we make the integral, we find RT natural log of V3 divided by V2. Therefore, this is just RT natural log of 7 V2 divided by V2, which is precisely, let's put here work 2-3, just RT natural log of 7. And if we calculate this, we will find that the work 2-3 is 0.287, which is R. That multiplies the temperature 2100 natural log of 7, and calculating this we find that the work is 1172.8 kilojoules per kilogram. And back to the ratio work. So the answer for part B, which is the ratio work, is going to be 516.6 divided by 1172.8, which gives us a back work ratio equals 0.44, and that's the answer for part B. And finally, part C. In part C, we need to find the thermal efficiency of this cycle. So let's put here, the thermal efficiency is given by the Greek letter eta, which is just the net work divided by the input heat in the process. So the net work we already have. The net work, let's put in here, is just the difference between the expansion work with the compression work. Therefore, this is just 656.2, okay? And the input heat we find, let's look on the PV diagram. So the input heat comes from the difference between the expansion work with the input heat in here, and that gives us the change in the internal energy. So let's put it in an equation. So we have K1 Q13, which is the heat, minus the expansion work, 3, needs to be equal the change in the internal energy, 13. Okay? Therefore, the change in the internal energy can be described as CV of T3 minus T1. Therefore, the input heat, which is equal the heat 13, is going to be equal CV equals CV that multiplies T3 minus T1 plus the work to 3, and this is going to be equal 0.718 that multiplies 2100 minus 300 plus 1172.8. Therefore, the input heat is going to be equal to 465 kilojoules per kilogram. Therefore, we can finally calculate what is the thermal efficiency of this cycle, which is going to be 656.2 divided by 2465, which gives us 0.266, or if we want, 26.6%. And that's the final answer to this problem. Thanks for watching.